with us today, we have Andreas. Andreas, he is the machine learning product manager at Encord. He has many years of experience working within medical imaging, and he spent the past 10 years researching computer vision and deep learning techniques in healthcare at the Institute of Cancer Research and Kheiron Medical. Sorry, Andreas. Today, Andreas, he will share his knowledge about some of the challenges health tech companies they face when working with medical images to build machine learning models. Andreas, over to you.
Thanks a lot, Nicola, for that kind introduction. I hope you can hear me. I will start sharing my screen now. Anybody can confirm that you can see my screen? Yes, that's good.
Looks good.
Great. You can also hear me, Cecilia? I take it as a yes. Cool.
Yeah, it's good.
Sorry, I can't see you. I can only see Nicola for whatever reason now, not the rest of you. I assume you're still there. As Nicola said, I'm happy to take a question during the talk. Just interrupt me and let me know what you would like to know. Yeah, going right into that. So let's kick off. If you work in medical imaging, the first question, the main question you need to ask yourself is, how do I get data to solve the problem that I would like to solve? And there are various sources for data around there. You probably stumbled over them, like public sources, databases where you can download data. You can use it for your own research. Always obviously check the legal terms there. And they will come in various formats and with various amount of data attached to it, like imaging data, clinical data, follow-up, and all these kind of stuff. So that's a good source to get started, to get going in the first steps in the first month or so. Obviously, you can also contact hospitals. They obviously acquire data during, let's say, a screening program. So a screening program is where people come in on a regular basis to have a medical checkup. For example, breast screening is a good example, or lung cancer screening. They come every 2, 3, 4 years, depending on the country. So the hospitals accumulated a lot of data, and they're obviously well aware of the wealth that they are sitting on there with the data. However, when you try to contact like a hospital, there's a big question how you're going to anonymize the data. Because depending on the country where you're in, you have to do certain anonymization steps. So you have to make sure that the patient cannot be identified in the data that you extract. And you have to prove that, obviously. And the question there is like, who's going to do the anonymization? And often, more often than not, the hospital don't have the knowledge or the capacity to do that. So you will either have to do that yourself, or you find a third party that can do that, and who's basically like a middleman who gets the data first, and then you get it for your purposes. The next question I stumbled over when we did that in the last 10 years or so for microscopic imaging or for radiological imaging is who's going to extract the data, right? Because medical image data can be quite big, right? For CT scans, it can be, let's say, a gigabyte or so per scan. And if you extract the last 5, 6 years from a hospital with follow-up data for patients, we talk about maybe a petabyte or so, right? So it's not a trivial process to extract data from the data amount, but also how you extract it, because it's normally in a so-called PACS system, which is a picture archiving system, a very long established way of storing medical data. And extracting data from there requires a lot of domain knowledge because a lot of this stuff is proprietary to the manufacturer. And these systems are normally designed that you store data and archive it for eternity, but not for extracting data, right? So this is quite a new requirement. So either have people who have domain knowledge, or you collaborate with one of the big manufacturers, let's say like Siemens or so, to get access to that system. Because when you start extracting stuff from there, you start messing around with the caching system, right? So the doctors there may not be very happy that they have to wait for their scans a very long time when they sign in the morning, because you started extracting data overnight from the last 10 years. So they have all the historical data in the cache, but not the most recent patients that they have to actually inspect. Moving on to dataset providers. So these are partners where you can buy data, right? So they may sell data, sometimes anonymized, sometimes not, depends where they are based. The good thing is they are normally well set up for you to get the data, right? So either get it shipped by hard drives or secure download links or something like that. And compared to hospitals, they also often know what they actually have and can query the data. I'm mentioning this because I've spoken very abstractly about data, but normally depending on your target, what you want to solve, you may require a certain group of patients, let's say in a certain age range, with a certain ethnicity, or with a certain, let's say if it's cancer, a certain tumor, right? And hospitals are often not able to query that. So they can give you a bunch of patients and a bunch of clinical records, but you will need to filter it out or something like that before you extract it. So this requires extra work. So getting to know dataset providers is quite handy, because you can basically give them a list of data that you require with all the features, and they hopefully can give you a reasonable quote and have the data. And last but not least, you can obviously generate the data yourself if you have the device, if you have something, if it's something that you can do in-house. So, however, that will take you quite some time, right, to collect and generate that data. And it depends on your use case, if that's feasible or not. If you develop, let's say, a breast screening program, breast screening solution, you probably won't be able to get enough data to train your models, but you may have something that's possible to do in-house. One important question that you have to ask yourself is what I'm getting, right? Am I just getting images, DICOM images, for example? Can they filter the data based on my request, or don't they have the technical knowledge to do that, or just not the technical infrastructure? And very importantly, do I get clinical reports? So do I actually get some easy parsable format of the clinical report that I can query and find out what's in the data, right? So an example would be, let's say, this is a cancer patient. This is a very high level report, right? A more detailed one would say this is a cancer patient with, let's say, 3 nodules in the right lobe of the lung, right? That may be better, right? Depending on what you're working on. Ideally, you get even location information like pixel data and masks where these, for example, malignancies are found. Depending where you reach out, there may be also a language problem, right? So these reports may be in a different language, so you have to think about how to translate that, how to set it up, because translation is not trivial of medical records. There's a lot of jargon, a lot of abbreviations. So you need domain experts who are like familiar in both the languages, the one you're working in, but also the language where you get the data from. Yeah, let's go through the data lifecycle, right? So when you start off in the beginning, right, you got your data. You're shown on the left side, any kind of medical data, X-ray data, microscopic data, or some radiological data. You more or less know if it fits your need, right? And you've got some annotators, maybe some in-house or something like that, or somebody who can email and say, "Can you have a look at this these DICOM files? What's on it? Is this useful or not?" And you will have most likely some workstation, probably in-house, or some cloud credits that you have where you can train a model, right? So that's where you normally do your proof of concept, or do the first stage of your product. And you soon run into bottlenecks, right? So you need to optimize these individual steps. And what people then normally do is, right, they scale the first thing, right? You can put it in the cloud. You can basically easily scale up the storage of the data, and they get more annotators, right? So you can scale them up too. This obviously takes a bit longer there, right? Because you need to find them, hire them, make sure that they have the domain knowledge. The GPUs, on the other hand, this is also quite easy, right? So it's a problem that can be solved with money. You buy more GPUs, you buy more cloud storage, so you can scale that up. But the real bottleneck, I think, is in the middle step here, right? So in the annotations, right? Because this is human based, and this cannot be easily scaled up like stuff that lives in the cloud. So this is the one where you normally run into problems when you need more data, let's say for a clinical study or so, and you have a tight deadline for some regulatory approval, and you need to generate a lot of annotated data to prove your concept. And that's where we come in, right? So you need some solution that also scales the middle part, that allows you to do annotations, that allows you to view files as they are. They don't convert it, that you don't get it converted, lose information there. And we have a platform where you can draw different types of annotations, yeah, like bounding boxes or polygons or segmentations. Or lines where you can separate things. And you have different tools, like a freehand tool where you can draw using the mouse or a tablet. We support tablets. Scissors where you can cut things off that you don't need, or a brush tool where you can start painting in and measuring stuff. Also very important because a lot of medical data comes in 3D. You need something to automate the labeling, right? Your experts are very pricey in medical imaging, right? So these are not these are normally domain experts. They have several years experience in the field to qualify for a project. So you really would like to make the most use of their time. And CT slices, for example, can be about 1,000 slices per patient if you have some thin sliced lung section or so, and you don't want them to annotate each individual slice. So what we offer is like a feature we call interpolation, where you can annotate, let's say, the beginning, the middle, and the end of a tumor, and the software does the hard work for you and annotates the slices in between. And we're also working on model-assisted support, where you can run so-called micro models. So you basically annotate a couple of instances, train a model within our UI, and then forward pass on the remaining slices to get some pre-labeling, because that's much quicker than starting from scratch. Also, ontologies are available, which in medical imaging are often called labeling protocols. Basically, like a tree, a recursive nested tree, where you can specify exactly what they should annotate, and if they find a certain instance, they can subclassify it what it actually shows. An example would be this is a lung, but then they can click, okay, this is the right lobe of the lung, or they can click then, okay, there's a malignancy in there, or leave even a text comment there for you to parse. Data normally comes in DICOM, right? So DICOM is a bit of a clunky format, so there are a couple of different flavors. And so other platforms often choose to convert that data, but conversion is always tricky in DICOM. So we made the step that we actually have a native DICOM rendering. So the data is rendered in your browser, so you can see the full extent of the DICOM volume. You see all the Hansfeld units there, so which is important for a radiologist because they are used to that when they annotate data on their screening monitor. And you can also view them in multiple views. Because it's 3D data, they normally expect an axial, coronal, and sagittal view. So basically, once slicing through the patient, but then also orthogonal views to see the other directions. And we also have maximum intensity projection, where you basically collapse the whole volume to a single image by taking the maximum intensities. Windowing support and hanging protocols, again, something that radiologists like a lot. Because over the many years that they have been working, they accumulated some muscle memory, how they view stuff, how they interact with the imaging. And we decided to basically copy that behavior so that there's a very low entrance barrier for them to interact with our viewers. I will pause here and just ask, are there any questions up to now? If not, I'll go to the next slide. So let's start with annotator strategies. So let's assume you have your data, right? And you will need to find out how do I get it labeled, right? Often companies started off, and that's also how I did it in the past when I was in a startup. You have some in-house annotation team. So it may either be a part-time or full-time person, maybe a radiologist, who is available for you for questions, and who you can task with the annotation process. This is obviously the most flexible option because the person is hired by you. He or she is very familiar with what you're building, right? So he knows also what you try to solve. However, it doesn't really scale, right? There's only so much the in-house radiologists can do, and you can't really scale up that process easily if you get like 10 times more data. So what normally we did is we look for external workforce, like some general labeling providers, right? But they label everything, right? From apples and pears and chairs and cars. If your task is easy enough, that's great, right? You may need to train them because they are not medical experts. However, they scale very well, right? They normally have a big group of labels available all over the globe where you can say, yeah, I need more, I need 10 times more. So the next step is normally external partners, like domain experts, people who offer medical labeling services. The good thing there is, you know, that there's you can basically request a person who has either just finished a degree or has significant knowledge in the field, like oncology or something like that, to do your task. This is quite important in medical imaging because a lot of tasks may sound easy for you if you're not a domain expert, but are quite tricky. For example, lymph nodes or something like that, right? So you will find a lot of examples of that in the internet, how they look like. But if you look through the CT scan, it takes a person with a significant medical knowledge to spot them and classify them. So it's then the only option to opt for this, some person with a medical knowledge. So the labeling workflow normally looks like this. In the beginning, you have to define a label protocol, right? That basically tells your annotators, labelers, what should we actually annotate and how. It has to be quite detailed, right? Because if you just tell them annotate something, there are many degrees of freedom how they could interpret it, like just a box or delineating the outline, or you know, just writing in text. Okay, there is something, right? So you have to be really specific. I found it very useful if you have a kind of a wiki page where you have screenshots or even videos of different structures and how to annotate it. I've got some examples in the following slides for that. And then normally we set off to send the first batch to the annotators, just get them hands-on. That allows them to get familiar with the tool, but also with the labeling protocol. How do they interpret it, right? And how do they go down with the tooling, and can they access it, right? And then you normally do a review, right? So you gather all the data that the annotators generated, and you have a look if they actually stick to the protocol. And you can also compute stats, like what's the concordance between these annotators, or simple summary stats. How many samples do they annotate in a certain amount of time? So you can get an estimate if you need more annotators to meet a certain deadline. Yeah. Then you normally go to train the annotators, because there will be some misinterpretation of the labeling protocol or some missed stuff. So you will find out and select annotators that fulfill your needs, and then you normally release the next batch, right? And what I realized in a product in a research development cycle is that the blue box here on this slide, this is a continuous process. You're never finished. Because if you expand to a different country or so, if you run for, if you go for another regulatory approval, there's always some data missing. Yeah? You need to prove that it works on a certain ethnicity. You need to prove it works on a certain group of people, let's say postmenopausal or something like that, that you haven't had access to before. So the blue box is something that it's an ongoing process throughout the lifetime of your product. So what's the labeling protocol? I start off with an example, right? Because when you talk to medical experts, they already have something in their mind what they have been doing in the past. And one common labeling protocol for oncology is RECIST. You may have heard about that. It's response evaluation criteria in solid tumors. So that's how they do it actually in their clinical workflow. So you see here a patient who has unfortunately several metastases in their liver, here in the first image, 1 and 2, 2 liver metastases. And you can see the protocol, the medical protocol requires them to delineate the longest diameter of the lesion. If you speak with the experts, obviously this is a tricky task, because this is an axial slice of a patient, right? And they have to find the slice where the tumor, the lesion is depicted with the longest diameter. This is not easy, right? It's very subjective, and they are aware of that. So, but that it's a trade-off between assessing it and the time that they have, because obviously they have many patients. And you can see, oh, this is a lymph node. This is barely visible, right? So that's why I said you need a trained eye for that. In 4 and 5, you can see some peritoneal metastasis that are delineated here with the longest diameter. And what they normally would do is they would do this for, let's say, a handful of lesions. And then they would compute the so-called longest, the sum of the longest diameters. So they will just sum up the longest diameter that you can see here, which is a kind of a measurement for the tumor burden, like the suffering of the patient, right? So that's what they would understand if you talk about labeling protocol at RECIST. That's what they are familiar with. That's what you need to think of when you write up a labeling protocol, because that's how they would plan for it, right? Bit more detail on that is like they would only annotate tumors with a certain size, minimum size. They would only go for a maximum of 5 tumors and a maximum of 2 per organ. And for lymph nodes, they would annotate the shortest axis, and then they would compute the sum of longest diameters as a kind of as a measurement for the patient. For tumors, here is it depicted again, the longest diameter, for lymph node, the shortest axis. However, you will also get follow-up data, right? So a patient will come more than once, and the tumor, a lesion, may break into 2 parts. So what they then do is they will have the follow-up measured similarly, like the initial, the base case, and they will compute the sum of longest diameters for that single tumor, knowing that these 2 instances here are actually the same tumor from the past that you have seen before. And that should give you a bit of an idea of what you have to think about when you start labeling medical data, because it's not like that you can say just draw and ellipse around the tumor, right? You have to think about all these cases. What if the tumor in the subsequent scan is like fragmented? So how do I capture that? Does my annotation tool allow that you can basically annotate the same tumor twice and say this is the same instance of the same tumor, because that's very valuable for you when you train a machine learning model, that it knows that this is the same tumor, and maybe predicting in a future case that this is actually the same tumor that it has seen before. Yeah, and that leads me to how to structure an annotation process, so the ontologies or labeling protocols. You see an example here from our platform for a lung cancer model. So we defined the class lobes, but when they delineate the lobes of the lung, they can click also which part it is. So you can see the right lung is divided in 3 different sections: superior, middle, and inferior, whereas the left one is only composed of 2 parts. This is important because a patient, depending on where the tumor is, has different life expectations. So this is great if you train a model, if you train a predictive model or something like that. You not only want to know where the lung is, but you also want to divide it into its sub-regions. And then there's another type here, for example, a nodule where you can say it is a malignant, benign, or unknown. And you can imagine you can have another nested entity there, where if it's unknown, specify why it's unknown. It could be blurry or something like that. So you basically have freedom of choice of what you want to do in these protocols, so you can and you get it nicely in a JSON, so you can parse it afterwards and query it. You should also think about the granularity level that you start off with. So initially you may think, oh, I just need the lung, right, for nodule detection. But later on you may realize you need the sub regions. So going through the data again is pricey, right? Because as I mentioned before, these are trained experts. So you want to capture as much as possible when you go through through these batches, rather than reiterating over the same data and say, oh, now that you found the lung, can you subdivide it? Mandatory features. Our platform allows you to specify that certain features are mandatory, because obviously when they go through several hundreds of cases, there may be something missed, but you really would like to know that there is something present, or that there is something not present for sure, right? So it's great if you can mention that. And normally I say avoid any free text, right? So especially for those categories that you need for your model, because there is a lot of difference in spelling, typos, or any other stuff. Like radiologists, when they look at an image, they will tell you a lot of other stuff that you see like a fractioner. So you're developing an oncological model, but they write something about fractions because they're so used to assess a patient in a very holistic way to write up everything that they can see there. So you really need to focus their time on the annotation process and what you want. And thereby also limiting the creation of new labels, right? So if you're interested in lungs and nodules, don't limit the amount of labels they can create, and so that they don't go wild and annotate other stuff that you don't want in your labeling process. This is a demo here of how to annotate an aorta. This is a CT scan, so you can see the aorta here, and I'm drawing now the outline of the aorta for the segmentation. Then I skip through a couple of slices. You can see the aorta moves slightly, right? And I'll then delineate another region here in the mediastinum, the aorta, the location of the aorta, and I will use the automated labeling that we have, where the platform will fill in the slices in between. So I tell the platform here that from slice 72 to 83, the aorta is present, and run interpolation there. So, and if I now scroll through these slices, you can see that the yellow outline is also in all those slices where I actually didn't delineate and the software did it. And you can imagine that that speeds up the process a lot when you have objects that normally extend over several slices. You don't need to go through each single slice. Here another examples about how labeling protocol can be misinterpreted, right? Because radiologists also assesses a sample for treatment, right? But you aim for some technical outcome, right? You would train a model, for example, right? So these are three real examples I have seen in the past. This is a breast sample, mammography sample, and you can see calcifications here. These are these white spots. So these are absolutely benign. There's nothing wrong with it. But sometimes, depending on the shape and the location, it may indicate that there's something going on, some cancer development. So it's great if you can annotate that, right? So, and on the left side, the first radiologist annotated it with a bounding box, basically indicating that there are two regions where there's calcification, right? This may be suboptimal for a model, right? Because you narrow down the search space, but you still don't know where there's a calcification. There's a lot of space in between that's not a calcification. So these bright spots here are the calcifications. Radiologists too interpreted the labeling protocol in a different way. Here she delineated like single calcifications, the larger ones, right? Because as I said before, in the RECIST protocol, they are trained to delineate a certain amount, not like an exhaustive annotation, right? So this is a bit better than the left one, right? Because you will get a more exact location, but there's still a lot of space around the calcification that's not actually calcification itself. The problem also there is if you train a model and the model detects this calcification here, you would say it's a false positive, right? Also, it's just not labeled because the radiologist skipped it. And you have to look out for those kind of things when you monitor your labeling process. And the right side one shows exact segmentations of calcifications, which you can obviously support with some micro models or something like that, so that you basically get the locations of each of these calcifications. I mentioned tooling, right? So it's important to train your annotators that they can use the tooling platform correctly. So here in this example, you see a mammogram, and I zoomed in there on a mass. So this is cancer, right? And you can see the outline here in this bright cloudy structure, and it's very, very spiky. It's called a spiculated mass. The shape, this is one of those things when I say the shape is important, so this is important, you want to capture that, right? So our tooling, our platform offers different tools, and on the left side you can see the person used the polygon tool, but didn't set the granularity level, the amount of vertices that you generate correctly, right? So you really need to train them that they use the tool in the right way, and your tool needs to support that you can actually capture the real shape of the object that you wanna train on. Because you can imagine, if I stop this video here, that your machine learning model will learn different things from like this smoothed outline, but it's smooth because of the annotation process, compared to this more accurate outline with the freehand tool that was drawn with a tablet. The next question is like, you need to schedule the right labeling experiments. So when you buy data, you will also get a lot of healthy data, right? For example, if you buy from a screening program. But are you actually aware what the prevalence of your disease is, right? So do you know how many samples will actually have the positive class that you would like to find in the data set that you buy? Because you not only want to have negative samples annotated where let's say the cancer is not present, you also need samples where there is the cancer present. So you need to be able to query that, and you need to be aware of that when you gather data, because as I said before, not every facility has the option to filter it down on what you want. Are you aware of how often you want to label data? Do you have a plan for that? For example, for training, sometimes it's enough if you label it only by one radiologist. And you get a lot of data in a very short amount of time. But for validation and testing, you may want to have it double, triple, or 5 times labeled, right? Because you not want to mimic the behavior of a single expert. You would like to have something that's more generalizable for a wider set of radiologists. You don't want to just automate one. You want to get a more objective opinion about that. So your labeling platform needs to support that. And for example, we can set up like double labeling experiments or something like that, where you can then compute a consensus, right? So assigning the label of multiple, or the majority voting of multiple experts rather than just one expert. And last but not least, one of the most important things is truthing, right? So what does this mean? So what do you call a positive class? So you can either derive from the labels, using the example before with the mammography, where there was a mass in there, right? So do you trust the labels? If somebody delineated a mass, then there is cancer in the image. Or are you looking for hard evidence, right? So you may also get like clinical reports where you have biopsy outcomes and surgery outcomes, right? So this is something where you would say there is like significant evidence that there was cancer, right? Because the biopsy said it so. But this is a very strong point for AI modeling and machine learning, right? So you can basically then say there was no label on it, but the biopsy proved afterwards that it was cancer. So you basically can develop a model where you can say, oh, we found cancer where actually the radiologist did not spot it, right? So this is a very powerful claim that you can make there using an annotation tool and hard evidence. Yeah, this leads me to some examples, some of our customers and collaborators. You probably recognize some of the names that are there. And it's really cool to see it out in the field and see it used. As Nicola said in the beginning, I was working for over 10 years in medical imaging, a lot of time on the side of the researcher, right, where I had to develop and design model or pass it through regulators. And now I'm working as a product manager here at Encord, where I actually try to solve that problem that I had the last 10 years to find an annotation tool that supports my needs, where I can annotate data, where I can track data, where I can schedule experiments, where I can basically scale up that middle part of the workflow. If you remember that from my first slide, you had the scale up of the data using the cloud. You can also get the GPUs via the cloud, but there's this middle part of the annotators that also needs to be maintained, because more often than not, people start off with tools like ITK Snap or something like that, right? Which works nicely for a handful of samples, or if you have enough resources to coordinate with each single annotators. But you need something more elaborate to scale it up. And these are some example customers. And I would like to go into two of them. Start with Stanford Medicine, where the division of nephrology was using our platform. and they noticed a significant speed up and a higher throughput in their annotation process. So they basically had a reduction in the experiments 80%, and they got through 3 times more images than without using our platform and our SDK, which I haven't highlighted yet in the talk. I think that's also a very strong point. When you look for an annotation tool, your engineering and data scientists, they most likely would like to have a programmatic interface to that tool, because setting up experiments takes a lot of time. And if you can do that with a programmatic way, and also setting up the ontologies and the labeling protocol in a programmatic way, it saves a lot of time, and it allows you to basically also track and review that process, because as I stated before, it's quite expensive getting medical images labeled. So you really would like to know where you are and how many samples you have annotated. There's also a reference here where they published it mentioning us and the speed up in the annotation tool. So that was a really cool project. And the next one is from King's College. And they had a significant increase in labeling of GI videos. They said it's about 6.4 times faster than the manual labeling, going through that through these endoscopic images using our platform. And we also supported them with automated labeling of these pull-ups. The last one is a quite interesting point. They said it's about 6x faster, 6 times faster, getting faster from getting the eye in production using our platform, rather than doing it with the tool set that they had access to before. Cool. Having said that, thanks for your attention, and I'm open for any questions.
Thank you so much. We have one question in the room here.
Yeah. Do you have any experience with MRI, sort of multi-sequence MRI?
Yes. Yes, it's a very good question. I have experience with MRI. Compared to CT, it's trickier, right? Because you don't have the Hounsfield units there, which standardizes the different images, the different volumes. So you will face problems depending on the version of the model, right? The software update that the manufacturer uses there, but also different manufacturers. So you have to spend a significant amount of time to homogenize the data in order to have a model that generalizes over different manufacturers over different time periods. So MRI is, I would say, significantly more different to work on and deploy, and have a reliable model out in real life than computed tomography.
So there's the Encord solution. Do you have anything that automates any of that curation or homogenization?
Yes, we do support MRI, so you can upload MRI images. We can talk about that in individual project, what kind of pre-processing we can do. We had some discussions and work done on CT already, so I think we could look into that depending on what you're looking for. Best get in contact with Nikolai about that.
The taxonomies that you talked about medical taxonomies or nomenclature. What those are external standards that you're referring to, or what?
Yes. So basically, they can mimic, for example, the RECIST protocol that I showed you, right, where you delineate the longest diameter and a couple of other criteria and measurements that you have to do. So you basically can integrate that, but you can also specify your own ones. So yeah, so there, and it's all tracked, the annotations. So you basically can use that tool to support your regulatory approval process, where you have to make sure that you know who annotated what and how long, and all these requirements you have.
I was more like thinking like Redlex or some other online database for labeling. I mean, do you use that, or what kind of? I think one of the early slides talked about standards and hooking up on external standards in the taxonomy for the labeling.
I didn't get the beginning of the question. Nicola, did you get the beginning of the question? It broke up.
I can see he's coming closer to the screen now.
Sorry.
I was just curious about the standardization of the labeling that you. I think one of the early slides mentioned that you hooked up to external standards. I mean, with taxonomies and what have you, with these hierarchical labelings. So you have a tumor, but you also have a glioblastoma and a glioma, etc.
Yes. So we can basically import different taxonomies, right? So you can specify it in a JSON format. You can import it and then basically roll it out to different experiments. So we are quite flexible there. So we can import predefined taxonomies. So up to now, it was flexible enough, or we could always make the change to support the labeling protocol of the customer who needed it.
Okay, so like rat legs or other like SNOMED or something like that.
I'm not familiar with SNOMED, but for example, BIRATS and these kind of protocols we support. I've set that up before.
Okay. Thanks.
Cool.
Okay.
Yeah. Thank you guys very much. I'll be sharing the recording with anyone who wanted to share it with anyone in their team. But if you have any questions, you can just let me know, or someone at the Health Tech Hub Copenhagen team. But otherwise, thank you and have a lovely afternoon.
Thanks.
Thank you. And thank you for having us.
Thank you.